Part 2 of the double angle identities. Here we're going to get into using these identities to help us solve more complex equations. So, I need to solve 6 sine x cosine x equals 1 for the domain negative pi to pi. Now, if you're looking at that, take out your list of identities, and on the list of double angle identities, look at the double angle identity for sine. That looks a lot like this, doesn't it? And if I divide this side by 3, I have 2 sine x cosine x. And that thing right there, this expression, that is equal to, by the identity, sine of 2x. We'll move that over here a little bit. Now that we have just one trig function, this is something that we can solve. We're going to use inverse trig. So 2x equals the inverse sine of 1/3. 2x, and this is something that we have to approximate, 2x is going to be approximately 0.3398 plus 2 pi k. Or the sign is also positive in quadrant 2, so 2x could also be 2.802 plus our good friend 2 pi k. Now we solve for x, so divide by 2 on both of these. We get x equals 0.1699 plus pi k. And this other one we get x equals 1.40 plus 2 pi k, or plus pi k. So what are our solutions? Well, our solutions are going to be, when k equals 0, we get 0.170, 3 sig figs, remember, guys. And we also get k equals 1.40. When k equals 1, if we add on pi to each of these, we get too big. We're greater than 3.14, but if we subtract pi from each of these, we'll get 2 more solutions. X equals negative 2.97, and also x equals negative 1.74. Remember, when approximating answers, you must give them to 3 significant figures. You will lose a mark every single time you don't do it on a problem on the exams. Next example, I want to solve cosine 2x equals cosine x for 0 to 360. Now, you might look at this and say, oh, those are the same trig functions. I have a cosine on the left, cosine on the right. But the problem is we're taking the cosine of 2 different things. It's not cosine x equals cosine x. That would be easy. It's cosine 2x equals cosine x. We need to make this thing agree before we can solve. We need to make the argument of this be the same for all the trig functions. So how can I do that? Well, look at your list of identities and look at the double angle identities for cosine. One of those identities involves only cosine of x. There's 3 of them, remember. There's one that has cosine squared and sine squared. There's one that has cosine squared and one that has sine squared. I want to use the one that only has the cosine. So I'm going to replace cosine 2x with 2 cosine squared x minus 1 equals cosine x. And I hope that you recognize this as being a quadratic equation. So 2 cosine squared x minus cosine x minus 1 equals 0. And if it helps, this would be an appropriate time to make the substitution of t equals cosine x. So then you can deal with the quadratic without having the cosine. I'm going to leave the cosine in here, though. This quadratic is factorable. 2 cosine x plus 1 times cosine x minus 1 so 2 cosine x plus 1 equals 0, or cosine x minus 1 equals 0. We can do a little bit of algebra here, and we know that cosine x is negative 1/2. And the nice thing is that's from our unit circle. We add 1 to the other factor, we get cosine x equals 1, and oh, that's also from the unit circle. So what are the angles where the cosine of x is equal to negative 1/2? Well, that's going to be in quadrant 2 and quadrant 3, and it's going to be a 60-degree reference angle. So what are those? Those are going to be x equals 180 minus 60, so 120 degrees, or 180 plus 60 for the quadrant 3 one, that's going to be 240 degrees. From this other factor, where does the cosine of x equal 1? It equals 1 at 0 degrees and 360 degrees. And there we go. Nice thing about this problem, this is a non-calculator problem. This is one that we should be and must be able to do without the aid of our calculator. The previous problem, because it wasn't related to the unit circle directly, the values that sine was equal to, that 1/3, that's not on the unit circle, that is something we have to approximate using our calculator. So what you've seen in these first two examples are questions that might appear on a calculator test and a question that might appear on a non-calculator test. And it's important to recognize when using technology is appropriate and when it's not as you're going through practice problems. Last example, what we're going to do is we're going to derive the double angle identity for tangent. The double angle identity for tangent. So tangent to x. If you want to know where we're trying to get to, go back to in your notes, look at what tangent 2x is equal to, and we're going to end up with that. So tangent is sine over cosine. Now we can use the double angle identities for each of these. Sine 2x is 2 sine x cosine x. Cosine 2x. Now, there's no right identity to use. We can probably get there using any of the 3 for cosine, but the one I'm going to use is the first one, cosine squared x minus sine squared x. And now if I divide, I'm going to move over a little bit, if I divide the top and the bottom by cosine squared, so I'm going to divide this by cosine squared x, I'm going to divide this by cosine squared x. So I end up with 2 sine x over cosine x over 1 minus sine squared x over cosine x, cosine squared x. And if we simplify, sine over cosine is tangent, and sine squared over cosine squared is tangent squared. And there is the identity that you see back in your notes. And this little example here is just an example for where this identity comes from. We build these identities off of other identities. I had to use the double angle identities for sine and cosine, and I had to use the identity for what tangent is. These things build upon each other to allow us to work with more complicated trig functions, and I just wanted to show that to you in this example.